In the previous video, we learned about forces. And we learned that there are several different kinds of forces we can identify that are useful for physics problems. Those forces included things like friction, air resistance sometimes. We talked about the normal force, gravity. We talked about pushing or pulling something, so you can exert a force on something. In this video, we're actually going to talk about how those forces that we identified can actually be summed up into just 4 fundamental forces. And actually, almost all of those forces I just mentioned are one type of fundamental force. And then there's another type that is very specific, but we use it all the time in physics. Okay, so I said there's 4 fundamental forces. One of them is extremely common, and it actually encompasses most of the types of forces we encounter in this kind of physics that we're doing. Another one's very specific, but it makes its way into a lot of physics problems. What about the other 2? Well, the other 2 forces are super important for nature and the world and the way things work. It's just we don't really use them in physics a whole lot, at least the kind of physics that we're doing. If you ever get into studying particle physics, you'll study those last 2 types of forces, and we're going to learn what those are today, but they're not going to be very useful, and you're going to see as we get into it, like they're super useful for explaining the world around you, and it's nice to know about them, but they're not useful for solving the kinds of physics problems that we're going to be encountering, very practical, real-world physics problems. All right, now, to understand the 4 fundamental forces, you need to understand what it means for a force to be fundamental. We say that something is fundamental when it is not made up of anything simpler. In addition to fundamental forces, in physics, we acknowledge that there are also fundamental particles. And it's important to understand what those are. You may be wondering from your chemistry knowledge whether the fundamental particles are the 3 basic particles you study in chemistry. In chemistry, you learn about protons, neutrons, and electrons. Well, one of those is a fundamental particle. 2 of them are not. And let's just get a good definition of what fundamental means here. Fundamental means it can't be reduced to anything more basic. So a fundamental force is a force that can't be explained by putting together simpler forces. It's just a force that exists on its own independently, the most reduced it can possibly be. There's no more components that make up that force. That force exists on its own. The same is true of fundamental particles. They're particles that cannot be reduced to simpler, more basic component particles. They just exist on their own. So I said that of protons, neutrons, and electrons, one of them is a fundamental particle. 2 of those are made up of components that are put together to make those particles. All right, well, let's go back to forces, and then we'll compare with particles. The 4 fundamental forces are the strong force, the weak force. Okay, these 2 are the ones that we're going to look into today, and they're interesting, but they are not ones that are going to come up a whole lot in the sort of physics that we're going to be doing. The 2 that do come up all the time, first of all, most forces are actually electromagnetic forces. We rarely think of them as electromagnetic forces. In a little bit, I'm going to give you an equation for how we calculate the electromagnetic force between 2 point charges. So like a positive charge and another positive charge, we can calculate the amount of force that they're going to exert on each other. We don't do that a whole lot. We don't think about it in terms of its fundamental nature. Instead, we think about things like you pushing a crate. Well, how are you able to push a crate? Your electrons and the atoms that make up you are going to repel the electrons in the matter that makes up the crate. And you're not going to chemically interact. You're not going to react with the crate and change your matter into something else. Your atoms are going to repel its atoms, and that's an electromagnetic force. We'll talk about that a little bit more in a bit. And gravity is the other fundamental force. That's the one that's very specific. Gravity is a very specific thing, but it takes place in almost all problems that we're going to be working because most real-world examples of physics happen on Earth or maybe some other planet, but they happen in gravity. All right, now, so I'm just going to circle the 2 forces that are the most common so we remember that these are the ones that we're going to be dealing with throughout our exploration of physics. The other 2 are nice to know about, but they're not ones that are going to come up an awful lot. The fundamental particles include quarks, All right, you may have heard that word before. Maybe you've never really learned about what quarks are. You'll be learning a little bit about them in this lesson. Leptons, that's a word you may never have heard before, or if you heard it in passing, maybe you've never learned what it is, but we're going to talk about leptons in a bit. And bosons, another word that may be familiar. There's been some fairly recent news about discoveries related to bosons. A lot of physics exploring bosons right now. Of these three fundamental particles, these are like the three buckets into which fundamental particles fit. You can identify more specific examples of quarks, leptons, and bosons. I'm just going to give you a couple examples you might recognize. A very common example of a lepton is an electron. An electron is a fundamental particle. A fundamental example of a boson would be a photon. You may have heard of photons before, little packets of energy. Photons make up light, electromagnetic energy, so they're what allow you to see things. These are the two fundamental particles that I'm guessing you maybe have heard about before. So I'm just going to circle those as ones that are common in both physics and chemistry. You may have also heard of quarks before. There's many different types of quarks that are fundamental particles also. But I circled the ones that you're likely to have come across before in your other studies of physics and chemistry up to this point. And we're going to dive in a little bit deeper with these today. It's important to know this. All of the fundamental forces are actually non-contact forces, which means that the actual atoms, the pieces of matter, aren't touching each other as these fundamental forces cause interactions. What does interact is energy. Energy can be transferred between the particles in little packets of energy like photons, but matter doesn't actually have to make contact for these non-contact forces to act. So that's what a non-contact force is. The agent doesn't physically touch the object, but the force can be transferred, and this is an important term, by force carriers, force carrier particles. Particles doesn't necessarily mean matter. It could be particles made up completely of energy, like photons. But that's the key to what these fundamental forces are. All of them are non-contact forces. And because all forces in nature are made up of these fundamental forces, there is no such thing as an actual contact force in the real world, really. Like the theoretical understanding we have of it is that nothing ever really makes contact with anything else. All forces act at a distance. Even when you touch something, yes, technically in the real world, in the macro perspective, you're making contact with it as you touch it, but partically what's happening is the particles of your hand that's touching something are just repelling the particles of that other object. So it's important for you to start thinking that way as you consider what's actually happening with the forces that we're dealing with. All right, so here's a video of an electromagnet picking up an object. Did you notice that the electromagnet didn't have to touch the object to lift it up? It just had to hover near it. And then when the electromagnet was engaged, there was a non-contact force that picked the object up. Here, we'll see that again here in just a second. The electromagnet's coming close, engaged, and it can pick the object up at a distance. Did you realize, though, there's another non-contact force occurring in this video as well? When the objects are released from the electromagnet, did you notice that they fell to the ground even without the ground making contact with them? This is an example of where non-contact forces actually come into play in the real world, and they're obviously non-contact forces. But really, all of the fundamental forces do not require contact. Let's take a deeper look at how this is actually working. So here's the picture of the moment before this engine hit the electromagnet. It's being lifted up. You can't really tell from the still. It looks like it might still be on the truck, or it might be touching the electromagnet. This is the best frame I could get of the engine in between. Okay? And what's happening to that engine? Well, there's our point in a free body diagram. I'm just going to put my free body diagram right over the image here so we can make sense of it. What forces are acting on this engine? Well, gravity is pulling downward. That's one non-contact force pulling downward on the engine that has the potential to accelerate it toward the Earth if it's a net force in the downward direction. But there's also an upward force, the force of the electromagnet pulling upward on the engine. And what's going to happen? Well, we saw what happened in the video. That upward force was greater than the downward force. So when I add the forces together to find the net force, I have a net force pointing upward. And acceleration always occurs in the direction of the net force. There is a net force here, so there's going to be acceleration. The acceleration of the engine is going to be upward toward the electromagnet. And then you saw what happened in the video. Accelerated upward, it collided into the electromagnet, and then it just stuck there because at that point the forces of magnetism upward and gravity downward were balanced. So the object was no longer accelerating, and in that case it was no longer moving against the electromagnet. If I were to identify the agents of these forces, the magnetic force is the force of the magnet on the engine, able to work at a distance, and the gravitational force is the force of the Earth on the engine, also able to work at a distance. Now let's talk a little bit more about that first fundamental force, the electromagnetic force. And this is a little bit of an on-the-nose example because I'm using an actual electromagnet to show the electromagnetic force. But keep in mind, there's all sorts of electromagnetic interactions that happen all day, every day, all around us. Right now, the light that is coming from your computer screen is traveling to your eyes in electromagnetic waves. The electricity that's running through the wires is doing so because of electromagnetic interactions. The electrons have an electric charge, and they're able to be manipulated based on that electric charge. Right now, as you watch this video, you're probably sitting in a chair. This is a very simple type of electromagnetic force. The atoms that make up you are repelling the atoms that make up the chair. Your electrons in your atoms are repelling the electrons in the atoms and molecules that make up your chair. So you're not falling downward into your chair. You're pushing on your chair, and your chair is pushing backwards up on you with a repulsive electromagnetic force. Electromagnetic forces are all around us in various different forms, not just with electromagnets like we had in our video, but from all different kinds of matter. And the thing that causes electromagnetic forces to act the way they do is photons. Photons are the force carrier for electromagnetic forces. They cause charged particles to interact. And that's why electromagnetic forces are so fundamental to all of the forces we experience in our everyday lives, is because almost all of the matter that we experience around us in our everyday lives is made up of charged particles that interact with electromagnetic forces through photons. And charged particles include protons and electrons, electrons again being one of the fundamental particles, but these are parts of atoms of all matter all around you. And that's why electromagnetic forces are so common, because they are occurring in all matter around you. And it's actually your main way of interacting with matter all around you. It's a way that you can apply forces to matter all around you through electromagnetic forces. So if we want to picture what an electromagnetic force looks like, and we want to use an electromagnet to do so, we could show electromagnetic forces by showing field lines where the photons are actually interacting around a magnet. Notice that these field lines come very, very close together and are very dense right by the magnet, and they spread out a lot further as you get further and further away from the magnet. And actually, as you get further and further away, the lines become more spread out and more parallel to one another, and they're not going to have as strong an interaction. Where the photon lines are strongest is where they're more dense in the drawing. And we can also picture the photon lines around charges like the charges around a proton or an electron. Let's put two protons next to each other and consider what the photons would look like that are going to cause electromagnetic interactions around the protons. So here's a proton. Here are the force lines around it where the photons are actually going to be interacting. Notice they're pointing away from the proton. That's because I must be putting another like charge next to it. Like charges repel. So here's my other proton, and here are the field lines around this proton. Notice that as you get closer and closer to the proton, the field lines become closer and closer together, and the force becomes more and more repulsive because it gets larger and larger the closer you get to the protons. All right, so let's consider this example because we actually have an equation that very easily deals with 2 point charges that are applying forces on one another, just like these 2 protons are. And the equation we have is the Coulomb's law equation. The electromagnetic force between these 2 charges is going to be equal to this constant, Ke, Coulomb's constant, times the size of both charges multiplied together. This would be a +1 charge for each of these 2, so it would just be 1 times 1 on the top of that fraction there, and then divided by the distance between the particles squared. Okay, so r is the displacement between particles, and that value is squared in the equation. So which of these values is the most important for affecting the force between 2 charges? Well, if you look at this equation, as particles become more separated, the force decreases by the distance squared, not just the distance, but the distance squared. So if you increase the distance between the particles by 2 times, the force decreases by 4 times. If you triple the distance, the force decreases by 9 times, but multiplies by 1/9. It becomes smaller and smaller, especially as the distance increases. And it's because the photons are more spread out. As the photons become spread out over a greater and greater area, which happens more as you increase your distance from the center of the point charge, the force is going to become less and less very quickly. It's called an inverse square law, and the electromagnetic force follows that inverse square law. Now, we're not going to be using that equation right now. It is an important equation to keep in mind, though, because it helps you to explain theoretically how these kinds of forces work. All right, now, what if we have an entire nucleus that has a lot of protons in it? Do you see any problem with the electromagnetic force in the nucleus of an atom? And here I've just taken the nucleus of one of the iron atoms that makes up the electromagnet that we're looking at. So this would be the number of protons, the number of neutrons in a typical atom of iron. How is it that this nucleus stays together? It's got all of these protons in it that are positively charged. There's nothing in the nucleus that's negatively charged. The neutrons are not negatively charged. They're neutral. Wouldn't all of these protons want to push away from each other with a great amount of force? I mean, they're packed into a very tiny amount of space. They're very close together. And the answer to that is yes. There is an electromagnetic force repelling the protons in the nucleus from one another, but yet the nucleus is sticking together. So what in the world is going on there? Well, there must be some other force holding the nucleus together. A very strong force indeed must be holding the nucleus together, and we actually call it the strong force because it is the strongest of the 4 fundamental forces. What's going on that holds the nucleus of an atom together? Well, remember, nucleus is made up of protons and neutrons. We call protons and neutrons a special type of particle in physics known as a hadron. All hadrons are made up of more than one quark. Okay, so protons and neutrons are actually made up of smaller particles known as quarks. And it's important to know there are 6 types of quarks, but only 2 of them really make up the matter around us in any appreciable way. Okay, so quarks are all fundamental particles, meaning that you can't break any of these apart into component pieces that make them up. However, a couple of them decay very quickly. They don't decay into like the parts that make them up, but they decay into other quarks that are more common. The 6 types of quarks have different charges, either a 2/3 plus charge or a 1/3 minus charge, and we can put them together to make protons and neutrons, which either have a 1 plus charge or a 0 charge, depending on which type of particle. And the First quark I'm going to mention is the up quark. The second one is the down quark. These are the two common types that we see most commonly in nature. Other quarks that exist, though, are top quarks and bottom quarks. Top quarks have a plus 2/3 charge, bottom quarks a minus 1/3 charge. And then the weirder ones, strange quarks and charm quarks, have odd names, but those are also fundamental particles. The two that we're going to be dealing with are up and down quarks. For now, we're just going to ignore the heavier quarks that don't exist in nature very commonly. We've observed these types of quarks. We know they're fundamental particles, but we don't really use them to explain how protons and neutrons behave, so we're just going to ignore them for now. What is a proton? Well, a proton, we know, is a particle that makes up an atom that has a 1+ charge. Protons are super important because they determine the type of atom and the type of matter that we're dealing with. If I were to take my iron particle and add another proton to it somehow, I would not have iron anymore. I would have a fundamentally different metal that behaves differently, and it would be identified as a different number on the periodic table. Iron has an atomic number 26, and if I added a proton, it would have an atomic number 27, which would change to cobalt, a metal that has completely different properties from the properties of iron, because now I've changed the charge of the nucleus of the atom, which is going to change all the electromagnetic interactions within the atom. It's going to have a different tendency to hold on to its electrons or give away its electrons. It's going to interact with other atoms differently than iron's 26 electrons and 26 protons would. So it's a big deal to change the number of protons in an atom. Well, what is a proton? How do I get a particle with a 1+ charge? Well, I can put together 3 quarks to make a proton. Every proton is made of 3 quarks in the same kind of arrangement. I'm going to have 2 up quarks and 1 down quark. And remember, each up quark has a charge of 2/3 plus, and then my down quark has a charge of 1/3 minus. And when I put those together, I get a 1+ charge. 4/3 minus 1/3 is 1. All right, what about neutrons? Neutrons are important for stabilizing the nucleus of an atom, and we'll see why that is in just a bit. Can I make neutrons out of quarks as well? Yeah, I can make them out of 3 quarks, the same as a proton. In this case, I'm going to have 1 up quark and 2 down quarks. The up quark has a charge of 2/3, each down quark minus 1/3, so they're going to cancel out, and my neutron is going to have no net electrical charge. So this is how I make up a proton and a neutron, but still I haven't explained why they are held together this way. In fact, if I look at these electrically, wouldn't the proton just blow apart because it has more positive charge than negative charge? At least the neutron sort of makes sense electrically. A plus 2/3 charge is going to cancel out the 2 minus 1/3 charges, so it looks like that should be electrically stable. But why isn't my proton just flying apart so the quarks are separate from one another? Well, it has to do with the strong force holding these things together. Quarks and protons and neutrons actually don't just interact electromagnetically, they interact a different way. They have 3 quantum states that we refer to by color. Now, these aren't real colors. You can't see these quarks. They're way too small. But we refer to them as their color state the same way as we just make up a way of referring to charge as positive and negative. Why positive and negative? Well, they're opposites. And the charges behave in such a way that when the opposites balance each other out, it's as if it has no charge. The same thing we do with these colors. We say that the colors are red, green, and blue, and when we mix them all together, we get white. Just like your computer makes white light and white images by mixing together red, green, and blue light at the same time. And what ends up happening with these particles is that when we do mix together red, green, and blue, the colors are balanced. And they sort of cancel each other out. They cancel out the color forces. I'm just going to refer to them as color forces. And they're neutral, and they're much more stable that way. These color states are constantly changing in atoms, but they are always balanced so that all 3 are present. these three quarks that make up protons and neutrons have to each have one of the color states. And then we say that the particle is colorless, and they have to be that way. And that's what makes the color force behave the way that it does, is that each of these three quarks that make up protons and neutrons are required to have one of the color states to be balanced, and it's in keeping that balance that these particles hold together. So here we have an example of the colors changing, but did you notice that at every moment one of the color states exists? There's something important to note here. Colors are not affected by charge. We have the charges existing in the particles. The colors are doing something entirely separate. And these color forces are actual forces that hold the particles together, but they don't rely on electromagnetic charge. There's something different. They're similar in the sense that we have opposites that are interacting with each other and holding together, just like positive and negative charges do. You're used to talking about positive and negative charges exerting force on each other. The same thing happens with these color forces. You have to expand your mind a little bit to envision what it would be like to have actually three different kinds of particles, and those three different states of particles are interacting to cause balance and hold things together. The force carrier that needs to be there is no longer photons, which we're familiar with, but a particle you may never have heard of before called a gluon. And what gluons do is they are able to travel between the quarks and change the color state of the quarks. And remember, these color states are constantly changing. That means these gluons are constantly traveling around. And because the gluons are constantly traveling through, carrying force, there's a strong force that holds the quarks together. So here's what this might look like. Here's a gluon particle. I just have it represented as a white particle. I don't want to put any particular color on it to be confusing here. And here are my three quarks. Okay, I have, if this is a proton, there would be two up quarks and one down quark. Or it could be a neutron with an up quark and two down quarks, but all three of the color states are present. And as my gluon makes its journey here, it's going to change the color states, and it has to keep doing that again and again and again and again to keep balance within the quarks. And as it's doing that, it's transferring force. There's a lot of energy present. It's holding the particle together. At this point, you may be thinking to yourself, wow, this seems really difficult to understand. And you wouldn't be alone. This is particle physics we're talking about. It is pretty complicated. Does it at least make sense, though, at this point, that the gluon making its rounds between the quarks that make up protons and neutrons, as it keeps balance and changes the color states in all three particles, is applying a force that is holding everything together? And it is an extremely strong force, so strong that the electromagnetic forces between same charged quarks don't have any impact. It's just a really strong force pulling the particle together. Hopefully it makes sense to you that that movement of the force carrier can apply a force that's like a rubber band holding the forces together, holding the particles together. Okay, now we've explained what holds the quarks together to make protons, and really what holds them together to make neutrons as well, although that one wasn't as hard to understand because the particles weren't repelling each other. But we have this strong force holding together protons and neutrons. We haven't explained what causes protons to want to be nearby each other in a nucleus, because these protons are electromagnetically repelling each other. So what's holding the whole nucleus together? You know what's holding the proton together? What's holding similarly charged protons together in a nucleus? Well, that has to do with a byproduct of the strong force called the strong nuclear force. Same force, different mechanism of action. And this one's even more difficult to understand than the previous, because in this one we have a very energetic reaction with the gluons. That's what's happening inside the protons and inside the neutrons. There's this very energetic reaction that actually causes a secondary interaction to happen outside the particles. So outside of our protons and outside of our neutrons. And what's going to happen outside of them, and we need a proton and a neutron for this to be happening, this happens with every neutron and every proton in an atom, we have these outside particles being formed. So see those, in this diagram, notice that the gluons are represented by two different colors flying between the quarks, and that's okay. That's another way of representing them. But notice what happens every so often when there's these gluon interactions. We have a new particle being formed outside the proton and the neutron, outside the hadron. And that new particle is called a pion. Okay, so what is a pion? Well, a pion is a type of hadron because it's made up of more than one quark, and it's able to participate in the color interaction. In fact, it's able to participate in the color interaction because of the protons and the neutrons together. So these protons and neutrons are now contributing to the forces that are holding the protons and neutrons together, and actually these interactions cause forces, the same strong interaction that are now binding protons and neutrons together. That's why you need both protons and neutrons in a nucleus to keep it stable, because there's more than just the electromagnetic force. And if you've taken chemistry or you've learned chemistry, you've learned that those electromagnetic interactions are key in a whole bunch of different chemical reactions and predicting how chemicals are going to react with each other, how matter is going to form, release energy, and things like that. But that's all electromagnetism. The other part of that that's important to understand is that atoms are held together because of an entirely different kind of force. These color interactions that are happening inside the atom. 3 different states that need to be maintained in every proton and neutron. Now, you may ask yourself, well, look at that pion. It's just made of 2 quarks. How can that keep the color interactions together with what we've talked about, how all 3 of them need to be present? Well, here's the thing. Pions are made of 2 quarks. One of them is a down quark and one of them is a down antiquark. Anytime you have an anti-something, that means that all of the quantum states are just the opposite. So instead of being a instead of being a negative 1/3 charge, like we would expect from a down quark, an antiquark is going to have a positive 1/3 charge. And when you put together a quark and an antiquark to make a pion, that means that the electric charge is going to be completely neutral. The other thing that happens with these is the colors are opposite. So you have one that's a color and one that's the anticolor. And that's the way that we explain that all of the colors needed are present. In other words, the colors combine to make a colorless hadron because just one is the exact opposite of the other. So you could have 3 combining to cancel each other out, or you could just have 2 different colors combining to cancel each other out if they're anti-colors. And then it's just important to recognize that this is the way that protons and neutrons together can participate in color interactions, and they can experience the color force. And they do. They do experience this strong force that holds the nucleus together. This force is very repulsive at short distances because it takes some distance for this interaction to happen. So at very, very, very extremely short distances, the protons and the neutrons are going to repel each other just a bit, and that's what gives the nucleus the size that it has. But this force is also extremely attractive at larger distances because we have these interactions happening, forcing the protons and the neutrons toward each other. So if you try to pull them too far apart, they're going to snap back, and the nucleus is going to remain intact in this way. All right, and that's the strong force. Now you know how the strong force acts to hold the nuclei of atoms together and to hold protons and neutrons together. The weak force is probably the least important of these forces for you to understand. I'm going to explain to you what the weak force is. The weak force is what causes beta radiation. Beta particles are just high energy electrons that are emitted when atoms decay from one type of atom to another. And this is only some types of radioactive interactions. All radioactive interactions have an explanation. Some of them involve the strong force. Beta decay involves the weak force. Here's how this works. A neutrino is a lepton that's very similar to an electron, except the difference between a neutrino and an electron is a neutrino has no charge. Can you imagine how hard it would have been for scientists to first detect that a neutrino was even a thing? Electrons are tiny. They almost have no mass. 1/2000th the mass of a proton or a neutron. But at least it has a charge, so it's pretty easy for us to detect because it has a 1 minus charge that's significant, that allows it to participate in forces that we can interact with. A neutrino not only is extremely small with a tiny mass, about 1/2000th the mass of a proton or a neutron, but it has no charge. So we can't even get it to interact by its charge. Now, what would happen if my neutrino released a positively charged particle? The positively charged particle is known as a boson, and it's actually the force carrier particle for the weak force. Well, if that happened, if my neutrino released something positively charged, and it was neutral before, then my neutrino is going to become negatively charged. And if it has the mass of an electron and becomes negatively charged, it must become an electron. So I changed particle types by releasing a W boson, and that boson is going to interact. It's capable of interacting with the particles, the quarks that make up a neutron. What's going to happen? Well, that boson is going to raise the charge of a down quark by 1. Okay, and I have a down quark that has a charge of negative 1/3. Now, if I raise its charge by 1, it's going to have a plus 2/3 charge. So what's going to happen to that down quark now that it has a plus 2/3 charge? Well, it must be, instead of a down quark, it has to be an up quark. And if I have two up quarks and a down quark in my particle, instead of a neutron, I must now have a proton. And this is one of the key ways that atoms change from one type of atom to another through radioactive decay. They can change this way because of the weak force caused by a neutrino. Now, I said that weak force causes beta decay, which ejects high energy electrons. Well, I have my electron here, and this electron is going to be ejected at a high speed from this interaction because it just absorbs so much energy as a result of changing a neutron to a proton. And this is what the weak force causes. It causes some types of radioactivity using a force that's different from the strong force. So we have to identify it as its own type of force, a weak force. Now, it's not really important for you to know about the weak force. We're not going to be using this in physics, not in the physics that we're going to be doing. However, this weak force is extremely important for how nature functions all around us. This is happening all the time in matter all around you that's changing from one type of atom to another. If too much of this happens nearby, this kind of radioactivity is dangerous and will cause problems for your health, but there is always this type of beta decay happening to an extent in the background radiation just in nature all around you. It's common, but not really important for our purposes. The last fundamental force is important for our purposes, and that is gravity. We observed gravity earlier on in the video of the electromagnet when the electromagnet disengaged and the only force acting on the engine was gravity pulling it downward toward the Earth. And when there's only one force acting, that force is the net force. There's no force really opposing the motion downward of this engine. And because there's no other force opposing it, this engine will be accelerating in the direction of the net force. So it's going to have a downward acceleration caused by gravity. Gravity does not interact with positive and negative charges. It does not interact with color forces. Instead, it interacts with mass. Regardless of the charge or the color, it's going to interact with mass. And anything that has mass is susceptible to interacting with gravity. In fact, anything with mass has a gravitational field. You have mass, so you have a gravitational field. It's just that the field is mostly negligible, even for very, very large objects that on Earth, like to the scale of city skyscrapers. They may have a measurable gravitational field, but it's not really going to impact things. You're not going to stick to the side of a skyscraper because it has so much mass and have to pull against the gravity of it pulling on you. Instead, you can measure the gravitational field, but you need extremely large objects, moon size, planet size, star size objects, to have significant gravities that are going to actually cause accelerations on measurable scales. We talked about a gravitational field. Let's take a moment to talk about what a force field is. A field, when we're talking about forces, is a space where a predictable force exists acting on a property of the object. With gravity, we're talking about acting on the mass of an object, but you could talk about the force, the electromagnetic force, and how the charge of an object affects the force on it within a field of electromagnetic forces. But in this case, we're talking about gravity, and the property that we're talking about is mass. And then regardless of the medium that it's in, this force is going to act. So it doesn't matter whether you're underwater, whether you're in the air, gravity is going to pull you downward. The air and the water are going to also exert separate forces on you, but the force of gravity is going to be consistent throughout the field, and we can predict how hard it's going to be pulling within that force field. Here's a picture of what the force field for gravitation looks like around the Earth. We just have a bunch of arrows pointing in toward the center of the Earth. And where the arrows are the densest, that's where the force is going to have the strongest gravitational pull. Where the arrows spread out more, the farther you get away from the center of the Earth, and I'm talking about significantly far away from the Earth. You're going into outer space, even on the International Space Station. We'll talk a little bit more about why weightlessness occurs on the International Space Station. There's still plenty of gravity there, but less gravity than there is on the center of the Earth. All right, so the gravitational field strength is actually expressed by an object's acceleration towards the Earth. And whenever you report an acceleration, 9.8 meters per second squared, you're actually reporting a gravitational field strength. We'll talk about another way of expressing the unit label for gravitational field strength other than meters per second squared, one that might make a little bit more sense. But anytime you express an acceleration caused by gravity, you're actually saying what the gravitational field strength is at the point where you're measuring that acceleration. And then technically, theoretically, scientists believe that there is a force carrier particle, probably made up of energy, just like photons are, but they believe there is a force carrier particle that causes gravity. That just like with the electromagnetic force, we have these photons that are moving through the field and actually interacting with charged matter, these tiny particles will interact with mass. It's just we haven't been able to detect them because they're tiny, and right now with the technology we have, impossible to detect. If we develop better technology, maybe someday we can detect gravitons. But right now, we don't know for sure that they exist. We haven't actually detected them. And then the equation for gravitation should look familiar to you because this looks very much like the equation for the force exerted by a point charge according to Coulomb's law. Fg is the gravitational force. G is a constant of universal gravitation, a fudge factor that changes our relationship between mass and distance into a correctly unit force. Then we have two masses that are multiplied together, and then the displacement between objects squared in the denominator of our fraction. So once again, distance between objects is the most important factor affecting the force of gravitation because that value is squared. All right, these are the four fundamental forces of nature and physics. So hopefully this gives you a better understanding what those forces are. And the two important ones, electromagnetic force and the force of gravity, are going to be the ones we are using in physics throughout the year.